In the last video, we derived the equation for a circle centered about the origin. In this video, we're going to derive an equation for a circle that has an arbitrary center. That is to say, it can be centered about any point in 2D space. So in the last video, we used Pythagoras' theorem to define a relationship between the radius of our circle and the x and y coordinates of any point on that circle. And we did that by saying the radius is that distance between the center and any point on the circle. And we've seen how we can find the distance between 2 points using Pythagoras. We construct a right-angled triangle. We know the lengths of the two edges, one that runs parallel to x, one that runs parallel to y, because of the coordinates of our point. And we know the relationship of those edges to our hypotenuse, our radius in that case, by using Pythagoras' theorem. And what that led us to derive is that the equation for a circle centered at the origin is x squared plus y squared is equal to r squared. But what if our circle wasn't centered at the origin? What if it was rather centered about some arbitrary point in 2D space that has the coordinates a, b? Well, let's take a look at what that might look like. And to save us some time, instead of drawing this all out from scratch, I'm going to make use of some layers I've already created. So here is our 2D space. Here's a circle centered at the origin. But what if we said it's no longer centered at the origin? It's centered some arbitrary position. And we know from what I just said a second ago that the center point of this new circle has the coordinates a, b. But what else do we know about this circle? Well, we know that still any point on this circle will have the coordinates x, y. And we know as well that the line that runs from the center of the circle to any point on the circle is a constant distance, a constant length, the entire way around the circle, and that length is known as the radius. So how can we relate these pieces of information together? Well, we've got the exact same scenario here. We have got the distance between 2 points, which is equal to our radius. How do we find the distance between 2 points in 2D space? We've done this so many times with Pythagoras, it should be second nature to us. We create a line parallel to x, a line parallel to y. We then know, because that's parallel to x and y, we know that it meets at a right angle, and using the coordinates of our points, we know how to work out the length of these edges. We've seen when we were finding the distance between 2 points in 2D space, to work out the length of our edge that travels only in x, we take the x coordinate of one point and we subtract the x coordinate of the other point from it. So that's going to give us x minus a. Likewise for y, we take the y coordinate of one point and subtract the y coordinate of the other point from it. That gives us y minus b. So we now have the length of two edges, and we know that relates to the radius of our circle. We can use Pythagoras' theorem. That is the relationship that defines how these three edges relate to each other. And that's going to give us the x minus a squared, i.e. the length of this edge squared, plus y minus b squared, i.e. the length of this edge squared, is equal to our radius squared. And this new equation is in fact the equation for a circle centered about an arbitrary point a, b. So fantastic, we found our equation, and we did it by using the same method that we applied for a circle centered at the origin, but we applied that to a circle centered at any arbitrary point. But we're not quite done yet. I'd like us to look at this equation a little bit further, because we've just derived that equation again using Pythagoras' theorem. But really what we've had to do is derive it from scratch. We started it completely again, analysing the new problem and deriving a new equation that matches that problem. But that could be quite time consuming in more complicated examples, and that might not be the best way to approach it in more complicated examples. So there is actually another way we could have thought about this problem to derive the exact same equation. Now this may seem a little bit confusing to those of you who aren't used to thinking in this way, and that's understandable and does come with time and it comes with practice, but please bear with the explanation and hopefully the logic will make sense, and hopefully by the end you can see where I'm going with this and how I get to the same equation. Now it's not essential to be able to do this, but I do think it is quite useful for other scenarios where you might be working with more complicated equations, and this may be the best approach for making a modification to the equation, such as no longer restricting something to be centered at the origin, for example. So let us consider our equation that we had before, which was for a circle centered at the origin. We know that that was x squared plus y squared is equal to r squared. So if we have that circle centered at the origin, and we had some other circle which had the same radius, but it was centered about a point AB, we're going to need to find the way to represent that circle somehow using this equation. So we've got, I'm going to draw a tiny little diagram. We've got our Cartesian space, we've got our circle centered at the origin, and then we've got some other circle that's a little too big, it should have the same radius, some other circle with the same radius centered about the point AB. So how are we going to be able to use this equation to represent this circle? Well, any point on our circle is going to need to be put into this equation and somehow satisfy the equation that relates it to the radius. But currently we know that isn't the case, because currently this equation requires the point to be on the circle centered at the origin. So what if we could take our circle that is out here floating centered around the point AB, and what if we could move that circle back so that it matches the circle centered at the origin? Because if we could move this circle back to the origin, surely then, if it's the exact same circle that is sat at the origin, we can use the equation that we know represents that circle to relate our x-coordinate, y-coordinate, and the radius of the circle. So how are we going to move this circle to the origin? Well, we need to move the center point of the circle from there to the origin, and to do that we need to translate in x by minus a and translate in y by minus b. We can see that if the center of our circle is AB and it needs to become 0, 0, then we need to take a minus a and b minus b to give us the center point of 0, 0. So we're translating by minus a in x and minus b in y. But if we're doing that to the center point of our circle, we'd better do that to any point that sits on our circle, because otherwise our points are still going to float out here, but our points need to also move so the entire circle moves. So what we need to do is apply that translation to our point as well. So the translation of minus a in x and the translation of minus b in y. So what we're saying is if we translate our circle back down to the origin, well, now that it matches the circle that's represented by this equation, we should be able to plug our coordinates into the equation and relate it to the radius of both of these circles. So there's our equation, x squared plus y squared equals r squared. Well, let's plug our x and y coordinates into it. So our x coordinate is x minus a, we're going to square that. Our y coordinate is y minus b, we're going to square that. And that is equal to r squared. Notice what we've got here. This equation is identical to the equation we found using Pythagoras' theorem. But what we've done is we've thought about it in a different way. We have thought about translating the coordinates of all of the points on our circle such that we can apply the generic equation for a circle that's centered around the origin to those points. You can actually think about it in a third way. You could also have thought that we translated our generic circle, as I hunt my tiny diagram, there we go, we translated our generic circle to meet our circle centered at AB. You can actually think about it in two ways, but both ways result in applying this translation to our points or to the equation such that we can use our more generic equation now to represent our circle centered at AB. So whether you want to think about using Pythagoras to define this or whether you want to take our previously defined equation and manipulate it, this is the equation that we're going to get. So I just wanted to point that out because I personally feel that translating a problem so they're centered about the origin, which then allowed us to use that more simple generic equation, is something we can do quite often in many different problems to make our life easier. And in fact, we're going to see in just a few videos time, when we intersect a line with a circle, just how much easier this can make our life by translating the problem so that it sits in an easier domain, if you will, so that it's easier to solve. We can make our life a lot more easy. So that's everything I wanted to cover with regards to the theory. So I'd like you now to try a couple of questions using our new equation. So the first question, and I'm not sure if I'm going to have enough room here, so I am going to bring up a new whiteboard just to be safe. Our first question, question 1, I'm going to tell you that the circle is centered at, so AB is equal to 2, 3. I'm going to tell you that this circle has a radius equal to 6, and that there's a point on this circle that has a y-coordinate equal to 5. I'd like you to tell me the 2 possible x-coordinates that this point might have. So go ahead and pause the video and attempt this. If you get stuck or once you've found the solution, unpause the video and I will work through the answer on the whiteboard. Okay, welcome back everyone. So what we're going to do is we're going to apply our new equation and put all of this information into that equation. So our new equation was x minus a squared plus y minus b squared is equal to r squared, and we need to rearrange this equation to solve for x. That should be something we're quite familiar with by now. So the first thing I'd like to do is get rid of this y term of the equation. So x minus a squared, let's subtract to cancel that addition, so is equal to r squared minus y minus b squared. So I've moved this over to the other side of the equation. Fantastic. Next up, let's get rid of this square on the brackets. So x minus a is equal to the square root of r squared minus y minus b squared. Now notice we're solving not to find a distance in this case, but to find some other value. In this case, we're finding the value of a coordinate. That means we must take the positive and negative square root. We can't just take the positive square root because we're not just finding a distance. We are indeed finding a coordinate value. So the last thing we need to do is get rid of that a. We can simply do that by adding a to our equation. So x is equal to a plus or minus the square root of r squared minus y minus b squared. So now all that's left to do is to plug our values into that equation. So x is going to be equal to a is equal to 2, so x is equal to 2 plus or minus the square root of the radius of our circle is 6 minus y is 5, b is 3, so minus 5 minus 3 squared. And now let's evaluate that. So x is equal to 2 plus or minus the square root of, and that radius should be squared, there we go, 6 squared, so 36 minus 5 minus 3 is 2, so 2 squared. X is equal to 2 plus or minus, so that's going to be 36 minus 4. Fantastic. So x is going to be equal to 2 plus or minus the root of 32. So I could accept 2 different values here. I could accept the sort of mathematically precise value if you were writing this down on paper. So that would mean that our x is either equal to 2 plus root 32 or it's equal to 2 minus root 32. These answers are perfectly valid. They are as accurate as you could possibly write them. But perhaps you were using a calculator to solve these values, to solve this problem. If you were using a calculator, then you may have got that x is approximately equal to 7.657 or approximately equal to minus 3.657. So in either case, whether you use the precise values or approximate values, you should have got something that looked kind of like this. And these are the 2 possible values for our x-coordinate such that a point with a y-coordinate of 5 sits on this circle. So that's question 1. I'd like to ask one final question for this video. So I'm going to bring up a new whiteboard. Question 2. And this question tells us that we're going to have a point that lies on the circle, and that point has the coordinates 4, 7, and our circle is centered at the point 8 minus 2, and what I'd like you to find is the radius of that circle. So go ahead and pause the video, give this an attempt. When we come back, I'm going to work through the solution. Okay, welcome back everyone. So again, we're going to be using our equation for a circle centered about AB. So x minus a squared plus y minus b squared is equal to r squared. Fairly simple to solve for r in this case. We're going to simply take the square root of both sides. So that's x minus a squared plus y minus b squared. We can plug all of our values into this equation. So x is 14 minus a is 8 squared plus y is 7 minus 2 squared as I scroll down. So let's now evaluate this. So 14 minus 8 is 6, so 6 squared, plus 7 minus 2 is 7 plus 2, which is 9, so 9 squared. So r is equal to the root of 6 squared is 36, 9 squared is 81. So r is equal to the square root of 117. So I would accept this as the most accurate value, but if you're using a calculator, that is approximately equal to 10.817. So if you got something close to this, or you got it is written as the root of 117, that is indeed the correct answer. And that is actually going to bring this video to a close. So again, to recap, we saw two different methods for deriving our equation of a circle centered about the point AB. The first method used Pythagoras to derive the equation much like we derived the origin-centered circle equation. The second used the idea of translating the problem so that we can use the generic equation to apply to that problem, which can also be thought of as translating the equation to match our more complicated problem. So there's a couple of different approaches, and as we're going to see in a later video, the idea of translating a problem so that we can use more simple equations is actually a very, very useful one and a very fundamental one for problem solving. But that is going to conclude this video. Thanks a lot, everyone.